Hello, all, and welcome back to Chem 131, Chemistry for Engineers at Southern Maine Community College. We will be working on Chapter 6, Periodic Table and Atomic Structure, and just a little bit of quantum mechanics tossed in. All right, so let's start taking a look at a few things here. First of all, we're just looking at the wave nature of light and electromagnetic radiation in general. So when we're working through this, let's identify a few things. First of all, we have wavelength, and the symbol for wavelength is this Greek symbol lambda. And that wavelength there is the distance between two peaks, peak to peak. You could also say it's the distance between two troughs. You could also say it's the difference between basically the same point on any two waves. So, like from there to there, that's your wavelength, and it's that distance. It's often, if we're talking about visible light, it's going to be in nanometers. So the thing to remember is that there are 1 times 10 to the 9th nanometers in 1 meter. Okay, now our next piece of information here is amplitude. And amplitude is the size or height of a wave. And here you can sort of see it here. Okay. And then the next piece that we'll be looking at is frequency. And frequency has, it looks like a V, but it's the Greek character nu. And this is lambda, if you want to kind of know how that gets spelled. It gets lambda. It might be lambda like this. Anyway, okay. And nu is the number of cycles of a wave passing a given point per second, and it's usually expressed in terms of hertz. Now, the thing here is that 1 hertz is the same as 1 inverse second. Okay, so seconds to the -1. And that's where that comes from. And what you can see here is that as your wavelength, so here we have a tight wavelength, and here we have a longer wavelength. So as lambda increases, nu decreases. They have an inverse proportionality. And last but not least here, we have the concept of velocity or speed. This is how fast a wave is traveling. And the speed of light in a vacuum, or C, is 2.99 times 79 times 10 to the 8th meters per second. So we'll be using that value quite a bit. Okay. Here we are. We are up to slide 3 so that I'm keeping track there. Okay, so the speed of light is the product of the frequency and the wavelength. Okay, so you get C is equal to lambda nu. So just kind of as a little reminder here, if you're going to solve for lambda, your wavelength, then you would do C divided by nu. And if you wanted to solve for nu, your frequency, then you would do C over lambda. So a lot of times you're going to be solving for a variety of things, and it's just how to work through that. Okay, now let's take a look here. So carbon can be detected in an X-ray fluorescence experiment by monitoring the emission of a wavelength of 4.47 nanometers. So this is much too small to see. It's outside of the visible light spectrum. And we want to know, what is the frequency of this light? Okay, so we've got a variety of steps here. Step 1 is going to be to convert our nanometers to meters, because your wavelength has to be in meters. So we have 4.47 nanometers. Okay. And we have 1 times 10 to the 9th nanometers. That'll go on the bottom here. And 1 meter. And so when we convert that, don't forget to be practicing this on your calculator, we will get a wavelength of 4.47 times 10 to the -9 meters. Now, our step 2 is going to be, we're looking for frequency here. So we'll use this equation. We'll solve for nu is equal to c over lambda. And because we're talking about the wavelength of light, we're always going to be using the speed of light, and that would be 2.9979 times 10 to the 8th meters per second, divided by our wavelength here of 4.47 times 10 to the negative 9th meters. Okay. Now, again, practice doing this on your calculator. It's really common for students to be putting this into their calculator incorrectly. So make sure that you are getting the same values I am getting. If you have a calculator malfunction on the test, it will cost you points. Okay. It doesn't matter if it's set up correctly. You do have to be able to do the math correctly. So be practicing this on your calculator. All right. We have 6.71 times 10 to the 16th. And you can see here that you have your meters canceling out, and you're left with this kind of inverse second is what you're left with here. Okay. And that's the same as saying seconds to the negative 1 or hertz. All right. So here we are. This is slide 4. Right. Now, electromagnetic radiation can be categorized in terms of its wavelength and frequency. And you'll get everything down from these gamma rays down here, gamma rays down to your long radio waves. And in this case, your wavelength, here's your wavelength right here. Here you have 1 times 10 to the negative 16th meters, all the way up to here, where we have 10 to the 8th meters. Okay, so that would be 1 times 10 to the 8th, or 1, that's a little easier to see, 1 times 10 to the 8th meters on this side. Okay, and that here in the middle, you have your visible light spectrum. Okay, and what we've done here is that this is anywhere from 4 times 10 to the negative 7th meters up to 7 times 10 to the negative 7th meters, or 700 nanometers and 400 nanometers. Okay. So all electromagnetic radiation travels at the speed of light in a vacuum. So for all of this, whether we're talking about gamma rays or radio waves or visible light, we're going to be using that C value of 2.9979 times 10 to the 8th meters per second. Okay. Now let's look at the particulate property of nature of light. Okay. So we find actually that light is not a perfect wavelength. It's not just a wave. It has basically these packets. Okay. And so light can only travel in these packets of h nu. You can't have 1.5 h nu. It's going to be h nu, 2 h nu, 3 h nu. And so there are nodes in between. And so what that means is that we have a very specific energy value for each photon. And this will give you the energy of a single photon of your light. And nu again is your frequency, and lambda is here. Okay. And you can either use E is equal to H nu. Use this if you have frequency. You can use E is equal to HC over lambda. Use this if you have wavelength. And the big thing to remember is that lambda has to be in meters. So make sure that you're converting. We will also be using H is a constant. It's called Planck's constant, and it's 6.626 times 10 to the negative 34 joule seconds. Okay. All right, and here we are at slide 6, and we're going to practice now. All right, so let's take a look here at slide 6. I'm back after a very short break. Okay, so chromium can be detected in atomic absorption spectroscopy by monitoring the absorbance of UV light at a wavelength of 357.8 nanometers. What is the frequency and the energy of a photon of this light? So here we are. This is really the only thing that matters here. Okay, and this is our lambda. Okay, so now let's take a look at step 1 is always going to be to convert this. So we have 357.8 nanometers. Okay, and we have to then convert this. Again, we're dividing it by 1 times 10 to the 9th. And this will give us 3.578 times 10 to the negative 7th meters. That's always got to be that first step there. Okay. And let's just take a look at this. We have 1, 2, 3, 4 significant figures here. Okay. All right. So now what we need to do first is it says, what is the frequency of this light? So we'll be using that nu is equal to C over lambda. And we have 2.9979 times 10 to the 8th meters per second divided by our lambda value, 3.578 times 10 to the negative 7th meters. And that cancels out our meters. And we get 4 significant figures here. So this becomes a frequency of 8.379 times 10 to the 14th. Okay. And that's going to be, again, in inverse seconds, which is the same thing as hertz. Now in step 2, now that we have nu, we can solve for E is equal to h nu. And so that's our Planck's constant, 6.626 times 10 to the negative 34 joule seconds times 8.379 times 10 to the 14th hertz, which are inverse seconds. And so now it's easier to see how your seconds cancel out. And you're just going to be left with joules. And this will give you a value of 5.552 times 10 to the negative 19th joules. All right, so now let's switch gears just a little bit. We're on slide 7, and we're going to start looking at quantum numbers. Okay, so first of all, the principal quantum number is known as, our letter for that is n, and that's the size and energy of the orbitals that we're talking about. And n can be integers, 1, 2, 3, 4, etc., and never ending. There are 7 n values on the periodic table, but you can go above that because you have orbitals available for excited electrons. Okay, so basically they're never ending, just the farther they get from the nucleus, the less likely they are. But these are the ones that are already established. Okay, next we have our angular momentum quantum number L, and it's usually kind of this cursive L value. And this is the shape of the atomic orbitals. It's sometimes called a subshell. Okay, the n value is sometimes called a shell. And it's the size and energy of our orbitals. This is a subshell, and it's the shape. And L is any integers from 0 to n minus 1. And when L is 0, we have an s orbital. When L is 1, we have a p orbital. When L is 2, we have a d orbital. When L is 3, we have an f orbital. And then we can actually keep going. If L was 4, we would have a g orbital. If L was 5, we would have an H orbital. If it was 6, it would be an I orbital, and so on and so forth. So here we're just following along with the alphabet after we get to F. The next one that we have here is M subscript L. I'll usually say M sub L or M subscript L, and that's right here. It's our magnetic quantum number. And this is about the orientation of the orbital in space relative to the other orbitals in the atom. And M sub L can be integers from negative L to positive L. Okay, so let's go ahead and just take a look at what an example of that might be. Okay, so if N was 2, okay, so let's say that N is 2. Okay, and I'm just grabbing a value here. Now, L are integers from 0 to N minus 1. N minus 1 in this case is 1. So you have two L values for this. You have 0 and you have 1 when N is equal to 2. Okay, now here it says M sub L are integers from negative L to positive L. So when L is 0, M sub L is equal to just 0. And then when M is equal to 1, M subscript L is equal to negative 1, 0, and 1. And this is what we mean by our orientations in space. Okay, so let's go ahead and take a look at this. When M sub L is 0, we have an S orbital. And if we have a three-dimensional coordinate plane and we have a sphere, there's only one possible coordination there. But when M sub L is when L is 1, we have three possible orientations in space. And so that might look a little bit like this. So this is a three-dimensional coordinate plane. So here we have on one axis, and here we have it on another axis, and here we have it on the third axis. And that's why we have these. And this will actually be PX, PY, and PZ. Okay, and it's P because L is 1 here. And we'll get to more of that a little later. All right, now we are here. We're up to quantum number 4. And this is our electron spin, M sub S or M subscript S for spin. Okay, it can be +1/2 or -1/2. So the way we'll often refer to that, though, is spin up and spin down. So every one orbital can have 2 electrons. Okay, and one of them is spin up or +1/2. And the other one is going to be spin down or -1/2. And that brings us overall to what we would call the Pauli exclusion principle or the Pauli exclusion principle. In a given atom, no 2 electrons can have the same set of 4 quantum numbers. So remember, those quantum numbers are N, L, M sub L, and M sub S. Every electron will have a set of 4 that is unique. Another way of thinking about that is that no 2 objects can be in the same space at the same time. So as we set up here, an orbital can hold 2 electrons, and they must have opposite spins. We say spin up and spin down, and spin up or +1/2, and spin down -1/2, and a down arrow. So let's take a look at how we fill in this chart. And you're going to fill it in as well. This is slide 9. And so let's take a look at what all of these are. All right. So hopefully you can see everything on the screen. My little picture here is sort of in the way, but that's okay. Okay, so first of all, our shell is going to be, remember, that's our principal quantum number N. Okay. And our subshell and designation, that's our L value. Our orbitals are that M sub L value. And over here, we have our number of orbitals And then we're going to have our spin value of m sub s. So when n is equal to 1, remember that L is from 0 to n minus 1. So that means that our L value is 0. And we have that 1 here. So let me kind of show you where that's going to come from. We have 1 here and 0 is S. So the designation is 1S. No C. Okay. Now, our M sub L value is from negative L to positive L, but when L is 0, we only have one possible value. That means that we just have one orbital, okay? And we could write it like this. We could write our electrons like this, spin up, spin down, and that gives us 2 electrons. Now, next, we have n is equal to 2. Okay, now we're always going to have our 0 and 0 and 1 and our single set of electrons here with 2 electrons. So every single orbital is going to have an L is equal to 0. Okay, but this one, because it's 2, is also going to have an L value equal to 1. And now this, because it's 2 here, this one is 2s and this one is 2p. Okay, but that means that our m sub L value here is negative 1, 0, and 1. So we have 3 orbitals. So that means that we could have one set of electrons and one set of electrons and another set of electrons for 6 electrons. Okay, now let's go through here. Everyone will have a 0. No matter how we do this. We always start with that. Every single row in our periodic table will have an s orbital. Okay. And as we come up, these later ones, will also have L is equal to 1 orbitals. So starting with N2, we will continue to always have p orbitals as well. Right. So you guys can keep filling this in. All right. Now let's take a look. Now, because this is 3, that means that we can go as far as L equal to 2. And M sub L is negative L to positive L. So now we have negative 2, negative 1, 0, 1, and 2. And that gives us 5 orbitals. So now I'm going to make half arrows here so that I have room. So we have 1 orbital, 2 orbitals, 3 orbitals, 4 orbitals, and 5 orbitals. Okay. And that gives us, I'm not sure how much room I have, but we have 8 electrons now. Nope, I didn't count that correctly. I did run out of room and I forgot. Okay, 5 orbitals and I only drew 4. Okay, so that means that we need another set here. There we go. Now I can see that we have 10 electrons. Okay, so, and I'm going to have that in n is equal to 4 as well. That L is equal to 2 value, negative 2, negative 1, 0, 1, and 2. For 5 orbitals, these are harder to make than they look on this screen. Okay, and here I have my 10 electrons for my 5 orbitals. Okay, now what this means, see, we have this 3 here. Okay, that means that this is 3s and 3p and 3d. Okay, so now let's finish our n is equal to 4. And you could just continue to do this. N is equal to 4 means that we're up to L is equal to 3, 4, 5, 6, 7, 8, 9, however many you wanted to go. And now we have -3, -2, -1, 0, 1, 2, and 3. And now we have 7 orbitals. Okay, so now I have to put in enough for 7. 1, we haven't talked about Hund's rule yet, but you can't do that. Okay. 1, 2, 3, 4, 5, 6, and 7. Ooh. Okay, and that gives us 14 electrons. And then if we're going to go ahead and fill through this, here we have a 4, so this becomes 4s and 4p and 4d and 4f. Okay. And like I said, you could keep going, so on and so forth. Okay. Okay, now let's take a look again. I started introducing the concept of orbital shape. So let's go a little bit farther with that. And we're up to slide 10 here. S orbitals are spherical. Okay, I'm going to go ahead and draw this because usually I'll ask you to draw them as well. Okay, so we have, whenever you have this, so we have y and, well, okay, this coordinate plane looks a little different. I'll go ahead and do them as I learned them. Y, X, and Z for our coordinate plane in case that's what you're more familiar with as well. Okay. Now, p orbitals, you can see they have these two lobes separated by a nodal plane. And a node is a place where your probability is 0. Okay. And when you're talking about p orbitals here, then you can have, remember, as I showed you before, you can have uh, p orbitals going in different directions because those are our different orientations in space. Okay. And then, okay. And that's why you have so many of them. Now, with the 4 lobes in the d orbital, you have 5 possibilities, and those are a little harder to draw. If you were going to draw them, I would kind of draw a clover leaf, sort of like so. And then call it good because it's hard to draw all 5. Okay, so those are our shapes. All right. So let's go ahead and take a look now at slide 11. And we're going to be looking at our periodic table at this point. Okay, so here we have slide 11. And you're going to note the order. So you can see this order 1s, 2s, 2p. Let me kind of, okay, let me go through that. So you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and that's because the d orbital is lower in energy than the p orbital, but the 4s orbital is lower in energy than the 3d orbital. So so this is the smallest energy or the lowest energy. And this is the highest energy here. And that's why they add out of order. Students will often ask me if it's wrong if they are out of order. And the answer is yes. If you do 1s, 2s, 2p, 3s, 3p, 3d, it will be incorrect. So it has to be in the correct order. And then 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So make sure that you have that order written down. Okay. And electron configurations are written in order of increasing energy for the atomic orbitals. So that's why things are out of order. Now, the periodic table is broken into S, P, D, and F blocks. The S orbitals are the alkali and alkaline earth elements. The P orbitals are group 3A to 8A, and you'll see that on I have a periodic table on the next slide. The D orbitals are our transition metals, and the F orbitals are going to be filled by our lanthanides and actinides. So you will notice that it mentions on here that you need to fill in your periodic table, and that is very important. So this is group 1 and 2, and these are our alkali metals and alkaline earth metals, and you can see that this is our S block. So over here we have group 3A, 4A, 5A, 6A, 7A, and 8A. Okay, helium goes right here. Go ahead and put that here. So helium, when we're talking about orbitals, goes right here instead of over there. Okay, and I encourage you to fill out your periodic table with this information as well. So here you can see I've marked the orbitals 1s, 2s, 3s, 4s, 5s, 6s, and 7s. And here we have over here 2p, 3p, 4p, 5p, 6p, and 7p. Starting here with the green ones, we have 3D, 4D, 5D, and 6D. And this is what you can see here. So here we go from 4s here. And then we have 3D here. And that's why it goes out of order, because these aren't up here in the third level. And then you have 4p here. Now, this periodic table shows that here you have 4f. Okay, and where did the 4f's go? The 4f's go right here, right there. Okay, between 6s and 5d. That's where they go. And then here you can see your 5f orbitals, and those are going to go right in there between your 7s and your 6d. And here at the bottom, you can see the order of fill again and how it links to the periodic table. So I would put this information right on your periodic table. All right, now let's take a look at the Aufbau principle and Hund's rule. And this is, we are up to slide 13. Okay. The Aufbau principle requires filling of orbitals starting with the lowest energy and proceeding to the next highest energy level. And so the Aufbau principle is why we go from 3p to 4s to 3d. And that's because 4s is lower in energy than 3d. And so the Aufbau principle tells us that that is the order that we need to work those in. Okay. Hund's rule states that within a subshell, electrons occupy orbitals individually and with parallel spins whenever possible. And what that really means is that, so for carbon, if we're looking at our periodic table, we see that carbon has 6 electrons. So it goes 1, 2, 3, 4. Now it's got 2 more electrons. And here we are in our p orbitals. There are 3 p orbitals, so they're going to go in separately first. They don't share until they have to. And so let's take a look at what that would be then for oxygen. And oxygen has 8 electrons. And so it fills its 1s orbital. And then it fills its 2s orbital. And now we have our p orbitals. So here we have 4, and so we're going to say 5, 6, 7, and then 8. And Hund's rule tells us that we have to do it in that order. So they place singly, and then they double back. Okay, so for the next slide, I want you to pick up your periodic table, and you're going to be looking at your periodic table while I am showing you how to do this. All right. So we have magnesium, phosphorus, and krypton, and this is asking us to make orbital diagrams and electron configurations. Okay, so let's see, this is slide 14. Now, magnesium has 12 electrons on your periodic table. And so we'll have 1s and 2s and 2p. And remember, there are 3 orbitals for 2p, and then 3s. Okay, now let's start placing our electrons. And I'm just going to use half arrows here because it's quicker. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means that my electron configuration is 1s2 because there's 2 electrons, 2s2 because there are 2 electrons, 2p6 because I have 6 electrons here, and 3s2 because I have those 2 electrons there. So this is what we would call an electron configuration. Okay, so now let's take a look at phosphorus. Phosphorus has 15 electrons. Okay, so I'm going to say, okay, now we have 1s, and that's got 1, and 2s will have 2. And then we next across the periodic table, we have our 2p orbitals. And then we will have our 3s orbitals and our 3p orbitals. Okay. Okay. Now let's see how far we're going to go now. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So our electron configuration will be 1s2, 2s2, 2p6, 3s2, and we only have 3 electrons in 3p, so that'll be 3p3. Okay, and I'm doing it based on the periodic table. Let's go ahead and take a look now at krypton. Okay, so krypton is number 36. So take a look at it on your periodic table. And again, if this is real something you're struggling with, this is definitely something that we'll be working on together in our in what we're working in recitation, in homework time. And actually, I think what I want to do with krypton is I'm going to X out of this for a moment, not completely. And we're going to go back to slide 12. Okay, now let's take a look here on slide 12 at our work. And let's do krypton here. Okay, so krypton is right here, number 36. Okay, now I'm going to basically identify the orbitals as I go. So until we get there, here we have 1s2. And I'm going to put it down here on our chart. And then I have 2s2, and I'll write that down below. If you can't see what I'm doing, I'm adding numbers to my order of fill down here until we get to krypton. Let me make this nice so you can see our target. All right, that's where we're going. Okay, all right. And after we go to 1s2, let's come over here, and you can see here, oh, I didn't mean to leave it quite so dark, so let's dial it back a bit. So here we have 2p6, and here you can see next we're up to 3s2, and now we're over here at the 3p's. We're getting closer to krypton, 3p6. And now we're down here to potassium and calcium. That's 4s2. And now, look, you can see that we're crossing over here. Okay. And that gives us 3d10. And here we are at the very end. We go 4p all the way to krypton, and then we're done. So 4p6, and we have completed that. Okay, so now let's take a look at and then we're done with our, sorry, I'm changing a bunch of little things on here. Okay, now we have our electron configuration, and we can go as far as we went, just like that. And then we're done with the rest of it. Okay, so that's another way of looking at that. So let's go ahead and from there, go ahead and toggle back to krypton. Okay, and we can make our orbital diagrams for that one. So we had 1s2. This is just what we came up with on the other thing. And then 2s2 and 2p6 and 3s2 and 3p6 and 4s2. Okay, and then 3d10. And last, we have our 4p6. I'll go ahead and sneak it in down here. Okay, and then we know that krypton is, that's what we got there. And so we can place our electrons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. All right, that was big. Okay, so now what we're going to do is we're going to take a little, we're just going to step back for a minute and look at our next slide. Okay, so this is to use our periodic table to find electron configurations for platinum, samarium, and bismuth. So what I'm going to do is I'm going to go back to that other slide where we were working, and we'll work on these. So you're on slide 15. Okay, so let's go all the way back here to this slide. You should have your periodic table next to you. Okay, and you're looking at slide 15 now. Okay, so now let's take a look here. Our first one that we're working with here is platinum. So let's find platinum. Platinum is number 78. Well, right here in our d orbitals. Okay, so let's work our way up to our d orbitals. And I'm going to put a little X where we are. So here we have 1s2 right there. Okay, and then we have 2s2 right there. And we have 2p6. I'm just going to put a little mark as I count them off. 2p6, 3s2, 3p6, and notice how I'm going all the way up to find platinum. Okay, 4s2. 3d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10, right like that. Okay, and now we've got 4p6. There's 6 elements here. Now we're in 5s2. Okay, and we've got 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoa, 4d10. 5p, we've got 6 electrons here in p, so that becomes 5p6. Now we have 6s2 right there. Now notice next comes 4f before we get to 5d. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that becomes 4f14. Now we're up to here, okay? And we have 1, 2, 3, 4, 5, 6, 7, 8 to get to platinum. So that becomes 5d8. It's not full. And we don't have any of these. None of these are full now. Okay. And that is our electron configuration. It's also very cumbersome. So what we're going to do now is we're going to say, okay, let's have some noble gas configurations as well. So this is we're still on platinum. And here's platinum. Now our previous noble gas here is xenon. So we can say, okay, here we have Xe for xenon. And that happens at 5p6. So our noble gas configuration would be xenon here, followed by 6s2, 4f14, and 5d8. And those are our full electron configuration and our noble gas configuration for platinum. Okay. Now on your sheet, you should see samarium. Okay, so let's find samarium. Samarium is higher than that. It's number 62 and it's right here in our F block. Okay, so let's go ahead and get down then to 62. And we have 1s2, 2s2, 2p6, 3s2, and I'm getting that right from up there in the periodic table. 3p6, 4s2, 3d10. One thing that makes it easy before, and I'll show you on the next one. So 3d10, and then we have 4p6, 5s2, 4d10 right here, because we're not, that's ends with 47 there. 5p6. Now we're down here finally in our row. Okay, we have 6s2, and then the next thing is 4f. 1, 2, 3, 4, 5, and 6. So that gives us 4f6, and we don't have any more. Now, again, we're from samarium here at 62. If we work our way backwards, xenon is our most recent noble gas at 5p6. Okay, so that gives us a noble gas configuration of xenon 6s2, 4f6. All right, now let's look at bismuth. And I'm going to teach you something slightly different for bismuth, another just way of working our way backwards. So let's go ahead and work our way backwards, and that's going to help us just another way of doing that. So bismuth is number 83, and it's right here. Okay, and what I'm going to do for bismuth then is I'm going to notice where I end. And you can see here at 6p3. See that? So I can say, okay, I end at 6p3, and now I'm just going to mark off what I have here, and that's all gone. And now I can fill it in backwards. If I start with 6p3, I can fill it in backwards, and D is full, and F is full, and S is full, and so is 6, and 10 for D, and 2 for S, and 6 for P, and 10 for D, and for S2, and we've got a 6 for the 3P, 2, 6 for the 3P, 2P, and 2's here and here. So sometimes it's a little easier, instead of thinking where it is to find out where you're ending and then work backwards from it. And I'm not quite sure how I did that, but everything works back to xenon here. And we come here to xenon, and our noble gas configuration then is 6s2, 4f14, 5d10, and 6p3. And you might say, okay, well, what are you doing there? And let me just go ahead and explain that a little bit more. So right here, what we start with is a full electron configuration. And that's really useful because that shows us your core electrons also. But down here, I have just the valence electrons, and I have a noble gas or valence electron configuration. And I will often ask for both. All right, these are not too bad when you get the hang of it, but sometimes they can take a little bit of time to get good at. Okay, so that was slide 15. So now we are up to slide 16. And let's take a look at some atomic trends. Okay. So when we're talking about the periodic table, we can actually predict some important things. So three of the things that we can predict here is we have, sorry, just trying to kind of figure out where I'm at. Okay, this we can predict atomic size. Sometimes this will be referred to as atomic radius. That's a lot of times what they describe instead of the volume. And this is the size of the atom. Okay. The next thing that we have is ionization energy. And this describes how easy or difficult it is to remove an electron from an atom. And then here we have electron affinity. And this describes how easy or difficult it is to add an electron to an atom. So electron affinity, bringing atoms to us, ionization energy, losing electrons. So let's start with atomic size. The shell in which the valence electrons are found affects the atom's size. Okay, so basically, size increases as we move down the periodic table. So here's our periodic table. As we go down the periodic table, we get larger. Because every n value is larger than the one before it. And that's basically because n is equal to 7, for example, is bigger than um, n is equal to 2. Okay. Now, the strength of the interaction between the nucleus and the valence electrons affects atomic size as this same row. So basically what happens is in a row, we're adding protons as we move across our periodic table. Here's my very funny periodic table here. So as we move across the periodic table from left to right, we're adding protons. Okay. Makes that positive charge increase. And that's going to pull the electrons closer and decrease the atomic size. So as we move across the table like this, we get smaller. The smallest part of the periodic table is up here. And the largest part of the periodic table is right here. And so you kind of have this overall trend that works in that direction for largest to smallest. Okay. Now we have this atomic size that we have in here. Okay. And your atomic size is showing you a few things here. Now, a green, let me go ahead and, so right here, green is row 1. So this is helium, hydrogen and helium. Okay. And then your purple ones here, sorry, that's row 2. So that goes from lithium to neon. Okay. And then let's take a look at more of these. In orange here, you have row 3. In this yellowy brown color, you have row 4, 5, and 6. And you can see this really perfect. Basically, it goes down. There's almost no exceptions to the rule until you get all the way up to row 6. Until you get to row 6, it's almost this perfect curve, even if it's not a perfect straight line. Okay, so now if we're ranking our elements in terms of increasing size, here we have iron, potassium, rubidium, sulfur, and selenium. Okay, so based on that, again, let's flip back to our periodic table. Whoops, I was going the wrong way. Sorry, guys. There we are. Here we are at our periodic table. Okay, and let's take a look at where we're at here. Okay, so here we have rubidium, which is right down here. This is, that's radium. Rubidium, where'd you go, rubidium? There we are. Rubidium is right here. Okay, and we have iron. Sorry, I remember that rubidium was on that list. We have iron, and here's our iron here. Okay, and we have potassium here, and we have sulfur, and we have selenium. Okay, so let's do this in order of our increasing size. Okay, so based on the idea that our smallest is up here and our largest ones are down here, then we can sort of do this connect the dots where we start with sulfur and then we move to selenium and then iron and potassium and rubidium. It's later like a dot to dot. So we would say that from the smallest to the largest, we have sulfur, selenium, iron, potassium, and rubidium. Okay. All right, now we're going to go down to slide right there, and we'll talk about ionization energy. Okay, so we're back here. We're talking about our ionization energy, and ionization energy is the energy required to remove an electron from a gaseous atom, forming a cation. And our trend here is that as we move from left to right, the protons are increasing, just like they were for atomic radius. Our protons are increasing, okay? And that's holding them in tighter, so it's going to take more energy. So it takes more energy to remove an electron as we move across the table, okay? And that means that our ionization energy increases. Now, as the valence electrons move further from the nucleus, okay, if this is your nucleus here, okay, and then here's your n is equal to 2, and then n is equal to 3, 4, 5, 6, and 7. By the time you get out here to n is equal to 7, you have this big negative electron blanket, and these electrons shield energy level 7 from being able to see the nucleus. So as we move down the table, it gets easier to remove an electron. That means that your ionization energy decreases. So this is a really great graph that shows you the first ionization energy in terms of your atomic number and your elements. Okay, so let's take a look at that. So you can see this overall trend here that kind of goes up like this. See how it goes up and up and up. Okay, so you can see these overall trends like this that are going up, but there are also these really, really important exceptions. Beryllium goes down to boron, and magnesium goes down to aluminum. And then you can see also right here, nitrogen goes down to oxygen, phosphorus goes down to sulfur. Okay. You can also see it a little bit here when you see zinc taking this nosedive down to gallium. Okay. And these are some really important exceptions. So why are they important? They are important because there's a couple different things going on. So from beryllium to boron, there's this slight decrease in ionization energy. And that's because beryllium fills its 2s orbital. But boron places a single electron in the 2p orbital. Okay. The 2p orbital is higher in energy than the 2s orbital, and it's easier to remove an electron higher energy levels. Okay. And so that's why we see a decrease from beryllium to boron. And in every time we go from 2 to 3A. And then here we have nitrogen to oxygen, and that's different. Nitrogen's p orbital has 1, 2, 3 in it, 3 electrons. They're all like that. But oxygen is the first one to double up. Now it's easier to remove. There's these 2 electrons have something called an electron-electron repulsion between them, and that lowers the ionization energy of that electron right there. It's easier to remove it because there's already an electron in that orbital. Okay, so now let's take a look at a little bit more practice. We are just about done. All right, so here it has us oops, sorry. We're going to be ranking these, and this is printed on your slide. I'm going to go back to that periodic table because we need to be looking at that. Okay, so here's our last slide again, and let's take a look at it. So first of all, the first one tells you to rank the following in terms of ionization energy. And here we have bromine, and we have fluorine, and we have gallium, which is right here on your periodic table, and we have potassium, and we have selenium. Okay, so what we can do, now we can really see that we can follow the dots. Now, the easiest one to remove is going to be this alkali metal right here. So we're going to start here with the potassium, and we're going to connect our dots as we go across the periodic table and then up to our top one there. Okay, so that means that if we're going smallest ionization energy to largest ionization energy, that we will go potassium and then gallium, selenium, bromine, and fluorine. Okay, now let's take a look at our next set. Okay, the next set, I'm going to go ahead and erase some of this, not all of it, some of it. Okay, so that we can take a look at what we have here. So what I have here is I've made a box. Silicon, phosphorus, carbon, and nitrogen. And those are what you're working with here. Okay, so now how do you kind of decide this? So we know from looking at this that from the way that silicon is going to definitely be our smallest, have our smallest ionization energy, and our largest ionization energy is going to be nitrogen. But how do they fall? Okay, so the way they fall is that they increase more going up than they do going across, which means that this will be silicon phosphorus and then carbon nitrogen. And that's how you will predict that. Okay, that's it for chapter 7. I will see you in class.